this lecture, we shall be considering the topic relativity, and this is our second lecture on relativity. So on this topic, we are going to start with time dilation, and later on, we would consider length contraction. Definition of time dilation. Time dilation is the slowing down of time for an object moving at a very high speed compared to an observer. The slowing down of time for an object moving at a very high speed compared to an observer. So in this context, we have two frames of references: an observer who is standing on the Earth's surface and another person who is in a spaceship. So it happens that the person that is in the spaceship, after embarking on space travel, suddenly returns back to the Earth. It would be observed that his own time would run slower than the time of the person who was on the Earth's surface. Let's look at this diagram here. So you can see somebody standing here on the Earth's surface. The time reaches the same point as the twin sister who is in a spaceship. Now, the one in the spaceship suddenly embarks on a journey, spends some time, and comes back. You see the one here on the Earth's surface here. Look at the time. So if I take this to be 5, all these pointers to be 5 minutes. So the one on the Earth here, we have 5, 10, 15, 20, spends 25 minutes waiting. Now, the pointer for the one in the spaceship is showing 5 minutes. What does that mean? The clock for the person who is inside the spaceship runs slowly. Are you following what I'm trying to say? So this is what is referred to as time dilation. Time dilation is the slowing down of time for an object moving at a very high speed, close to the speed of light, compared to an observer. Are you following me? So let's see other points that we have here. Imagine two identical clocks. One clock stays on the Earth. The other clock is inside a fast-moving spaceship. When the spaceship returns, the clock on the spaceship shows less time has passed. When the spaceship returns, the clock on the spaceship shows that less time has passed. This means moving clock runs slower. So that is just the idea behind time dilation. So when you have an object moving at a speed of light, time in that object slows down relative to the one we have on the Earth's surface. So the equation is written on the screen here. So if you don't use the first equation, you can use the second equation. They both have the same meaning. So change in t here means time measured by the observer. So the observer on the Earth's surface has the time change in t. Then the proper time, or you can call it time measured by the moving clock, is t naught, change in t naught. Then u is the speed of the object, and c is the speed of light. The Lorentz factor is the symbol you are seeing here, and the Lorentz factor is the same thing as, I think, anyway, let me scroll down, you will see the equation for the Lorentz factor. So the Lorentz factor equals to 1 over square root of 1 minus the velocity of the object, the square of the velocity of the object divided by the square of the speed of light. Alright, so if we go back to this equation, you can see that they mean the same thing. So for equation 1, here we have the Lorentz factor and the proper time. So if we don't write it as equation 1, we can as well present it as equation 2, knowing that the Lorentz factor is the same thing as 1 over square root of 1 minus u square over c square. Are you following me? Alright, so let's move on. We've already considered this. Example 1. This example says, a spaceship moves at 0.6 c, that's the velocity of the spaceship. The astronaut measures 8 seconds, that's the proper time, or I should call it the time of the spaceship, the time in which the astronaut covered. Now the question says, how much time is measured on the Earth? So we want to find the time the observer measured on the Earth. Alright, so we are going to use both equations so that you get proper understanding. Anyone you are comfortable with, you can apply it. So let me start with this other equation here. Let me use my pointer. Alright, so I am going to start with this very equation. Alright, so we have here a spaceship move at, so this is the velocity of the spaceship. So this is u. The astronaut measures 8 seconds. So this is t naught. We are going to substitute 8 into t naught, and then u, we are going to substitute 0.6 c into u. Of course, we know that c is the speed of light and the value is the same. So instead of us substituting the value for the speed of light, we are going to cancel out. Alright, so we proceed. Substitute the value here. So t naught here we put 8. We have 1 over u square. In place of u square we put 0.6 c. Now there is a bracket here, so to clear this bracket we are going to multiply this power here, this index, by c here, and we also multiply this index by 0.6. So when we do that, what do you see? We would have 8 divided by square root of 1 minus 0.6 square. This becomes 0.6 square and c square divided by c square. So you can see that c square is common to both sides, or the numerator and the denominator. So this will cancel this. So what will be left is 8 over square root of 1 minus 0.6 square. Okay, so this is what you will see. When you simplify that, it will give you the time of the observer on the Earth's surface. So you see that the observer on the Earth's surface, the time of the person who is observing is 10 seconds, while the time of the person, the astronaut, the time in which the astronaut measures is 8 seconds. The slowing down of time when an object is moving close to the speed of light. We call it time dilation. So please memorize this equation. We can as well use this other equation, but what we would do first is that we will first simplify the Lorentz factor and then multiply by the time of the astronaut or the proper time. So let's see how that is done, because you are going to solve other examples. The same problem here, and we are going to apply this other equation now. So firstly, we are going to now simplify the Lorentz factor and then multiply by t. So you know the equation of the Lorentz factor. When you simplify it, substitute the same way I did the other one. You arrive at 1.25. See what I mean? The Lorentz factor is equals to this value here. Alright, so substitute 0.6 C into U and simplify. You will get this. Just try it by yourself. Now, we have the Lorentz factor to be 1.25. So here, you now come here, you see T0, the proper time, which is 0.8 seconds. So when you multiply this by not 0.8 seconds. When you multiply this by 8 seconds, you will get the t that we are looking for. Alright, so let me just do that. Step 2. T equals to the Lorentz factor changed in t. We have already solved for the Lorentz factor. Then we now multiply by 8. So we get the time of the observer on the Earth's surface. Alright, please, if you are yet to subscribe to this channel, please endeavor to do so. If you have done that already, please like and comment so that other people can as well see the channel. Thank you very much. We are still going on to example 2, time dilation. This other example says a particle moves at 0.8 c. That's the velocity of the particle. Its proper time is 15 seconds. Find the time measured by the observer. So we have the velocity of the particle here given, and we have the proper time, which is T0. So we are to find the time of the observer. We are still going to use the same equation as before. So, but this is the equation of the Lorentz factor. Alright, so in place of U, we are going to put 0.8 C, and then we simplify. When you do that, you will get 1.667. Alright, the Lorentz factor does not have SI unit because it is a ratio. So the units will cancel out. Now, to get the time of the observer, we apply this. So we are going to multiply 1.667 by 15 seconds. So we get 25 seconds. So the observer observed 25 seconds on the Earth. Yes, 25 seconds on the Earth, while the astronaut observed 15 seconds in the spaceship. So you now see that slowing down of time when an object moves relative to the speed of light. It is referred to as time dilation. Alright, we can as well use this other equation. If you apply this, it will take you down to the solution directly. Please, I would like you to do it. Just do it so that you master it. That's why I decided to simplify my lecture this way, so you can apply it. I have other examples or assignments here. You can just solve it and let me know what you have been able to come up with on the comment section. Here we have the Lorentz factor. Question on Lorentz factor. Find the Lorentz factor if u is 0.7 c. So when you solve it, compare your answer to this and see if it is the same. If it is not, you try again. Then the second question, find the Lorentz factor if u equals to 0.9 c. Also compare your answer if it is the same. Let's quickly move down to the other topic, length contraction. Before I continue, please look at this diagram here. You see an observer standing here and a stationary train. This train, let's say, is 100 meter, for example. Now, if this train suddenly moves at a velocity close to the speed of light, this observer here will notice that the length, or it will appear to this observer, let me put it that way, it will appear to this observer as the length of this train is shortened, and as such, this observer might notice something to be about 80, or the length to be about, let's say, 80 meter, as the case may be. Alright, so this what we refer to as length contraction in relativity. So length contraction means that an object moving at a very high speed appears shorter in the direction of motion. And of course, this object will tend to move at a speed close to the speed of light. So the length contraction means that an object moving at a very high speed, close to the speed of light, appears shorter in the direction of motion. Simple explanation. Imagine a train that is 100 meters long when standing. If it moves close to the speed of light, an observer beside the track measures it to be shorter than 100 meters. That was what I was trying to say. Only the observer sees the shortening. The passenger inside the train still measures 100 meters. So the length contraction has nothing to do with the train. It's just an observation. So the observer who is standing outside the train sees the train to be shortened, the length of the train to be shortened, but the person who is in the train does not observe anything. So the formula is L equals to L naught root 1 minus u square over c square. Of course, we know that this, anyway, let me continue. You can as well define it this way. Okay, where L is the observed length, L naught is the original length or the proper length, u is the speed of the object or the train, the Lorentz factor, and all of that. So let's take the first example here. A rod has a rest length of 1.0 meters and moves at a velocity of 0.6 c. Find the observed length. Alright, so we are being given the rest length to be 1 meter and then the velocity of the moving object here. Alright, so using this equation here, you can see that the original length, the rest length, is L naught. We also have 0.6, which we are going to substitute here, and then we cancel out. So this is what we have. L equals to 1.0 root 1 minus 0.6c. Now, there is an index here. So this will be multiplied with this and also with this. Of course, if you do that, you will have 1.0 root 1 minus 0.6 square 0.6 square c square all over c square. So this will cancel this. Are you following me? So now the equation reduces to this, because when you square 0.6 square, you will get this and all of that. So you simplify it, you arrive at 0.8 meters. Alright, so the question says find the observed length. So the length of the observer is 0.8 meters, but the actual length of the train is 1.0. So the person now sees length contraction of the train. Okay, example 2, a space probe has a rest length of 18 meters and move at 0.8 c. So for us to find the observed length, we have this, we use this equation. Please try it. So where you have L naught, you're going to put or substitute the value here 18, and of course where you have U here, going to substitute this. When you simplify it, you will now arrive at 10.8 meters. You see that there is a reduction in length. Let me take it that way. There's a reduction in length from 18 meters to 10.8 meters as observed by the observer. Alright, so this our assignment. I'm giving you question 1. A train is 50 meters long at rest. It moves at 0.6 c. Find the observed length. So compare the answer with the one on the screen. You solve it and check if you have gotten the correct answer. Example 2 or question 2. A rocket is 25 meters long at rest and move at 0.8 c. Find the observed length. Please, thank you for watching. Have a wonderful day.